So let's continue with the third part of this talk, bifurcating minimal surfaces with symmetries. This, as a reminder, is a talk in 4 parts. This is part 3, in which I'll discuss minimal spheres in 3 ellipsoids. Okay, so using the same notation that we had in part 1, E, A, B, C, D will denote a 3-dimensional ellipsoid sitting inside R4 with these semi-axis A, B, C, D, which are positive numbers. And there are some obvious minimal 2 spheres sitting in there. They are actually totally geodesic, and they are given by intersections with hyperplanes. So that's why we call them planar. They're planar minimal 2 spheres given by intersecting with the set xi equal to 0 for each I from 1 to 4. Of course, these are fixed point sets of reflections about each of the axes, and therefore they're totally geodesic spheres, hence minimal spheres. So the question of Yau that I mentioned in the first part of the talk was whether there exists any other embedded minimal 2 spheres inside these 3-dimensional spheres. And the main result for this part, this third part right now, is the following theorem obtained together with Paolo Piccione last year. If we assume that either B is equal to C or C is equal to D, meaning at least 2 of the semi-axes agree, then the number of distinct non-planar embedded minimal 2 spheres in this ellipsoid grows to infinity. It actually goes to plus infinity as A gets large. Okay, and so for each finite value of A, there's only finitely many minimal 2 spheres up to congruences. That, for example, comes from Troy Schoen. But the number grows as A gets large. So in this picture, you can imagine A is this distance. As the ellipsoid elongates, more and more minimal 2 spheres will bifurcate from one of these planar minimal 2 spheres. For example, here, this would be pi 4 in that picture. Okay, not only that, these bifurcating solutions, which are represented here by these yellow curves, they slowly make their way to the middle. And, all of these points kind of come together and converge to a multiple of this minimal sphere, which in that notation would be pi 1, the shortest one, the smallest one of them, so the one obtained by setting x1 equal to 0. So these minimal 2 spheres in yellow, they converge there as A goes to infinity, even as graphs. Okay, they converge as variables, but actually can prove graphic convergence away from a couple points. All right, so of course they converge with multiplicity, right? For example, here this yellow guy goes around twice, right? Eventually converges to it with multiplicity 2, and the other ones will converge with even higher multiplicity. So we can actually even give more precise information if, say, I set B to be equal to C, so we have something a little more concrete, then the lim-inf of the number of distinct solutions, distinct non-planar minimal 2 spheres, meaning up to congruences, divided by A, this is bigger or equal than 1 divided by 2D. Okay, 1 divided by 2 times the smallest semi-axis. All right, so in order to discuss the proof, I'll give a sketch of the proof in the remaining of this part of the talk. Let's recall the symmetry reduction setting that we'll use, which is based on the Xiang-Lawson reduction that I discussed in the first part of the talk. So let's color code a few things here. Let's use Z2 in blue to denote reflection about the x1 equal to 0 hyperplane. Then I want to have an O2 component here of the isometry group, which is the O2 acting by isometries on the x2, x3 plane. Remember, because I'm setting B to be equal to C, let's fix that choice. Any rotation here is an isometry of the metric. And there's another Z2 in reflecting x4. So the group that we'll be mostly interested in is the O2 in orange, this O2 that rotates these 2 coordinates. So of course, if you look at the g-orbit of a point, x with coordinates x1 through x4, this is the circle that you obtain. This is a circle provided, of course, that the radius here is non-zero, right? Otherwise, it's a fixed point. So there's some fixed points. For example, if both x2 and x3 are equal to 0, you're not rotating anything, you're stuck at a circle, you're stuck at a point. So these are these fixed points. So the set of fixed points is the intersection with the points with x2 and x3 both equal to 0. And the principal part of S3, the principal points, as we discussed in the first part of the talk, they are everything else. So the complement of the fixed point set, in this case, is the principal part. Remember this open dense and connected subset. In this case, it's everything except for this circle worth of fixed points. So then it's not too hard to see that the Riemannian metric induced in the quotient, such that the projection map here is a Riemannian submersion, that Riemannian metric is precisely the one induced on the disk, on the two-dimensional disk, by realizing it inside three-dimensional space like that, as a hemisphere of an ellipsoid. So algebraically, what you're doing is really pretend you take these two coordinates and you replace them with r squared over b squared, right? And that's the new equation you got. And r is non-negative. R is actually the radius of that circle, okay? So, so I claim here, this is exactly the orbit space up to isometries. Notice it has boundary. So the boundary is exactly the set of fixed points, which, let me try to write this a little bit better, which is the set where r is equal to 0. So you can picture here r being the height function, like the z-axis here. And this would be x1, that would be x4, okay? So the boundary is over there. These are the fixed points. Of course, the volume of principal orbits, the volume of a circle of radius r is 2 pi r, right? That's its length. If you solve for r here, you see that it can be written like that. So it's precisely 0 on the boundary, as we had discussed in the first part of the talk, okay? And it's positive on principal orbits, but 0 on the boundary because the dimension drops. In this case, they are actually fixed points. So omega A will denote the Riemannian disk obtained by setting here a conformal factor in front of this metric. The conformal factor is the square of that volume function. For the reason that we discussed before, that if we are looking for minimal surfaces, these are exactly minimal surfaces downstairs when I put that conformal factor. So if I want a minimal sphere, I actually will need to find a free boundary minimal geodesic, or free boundary geodesic, free boundary minimal hypersurface, meaning free boundary geodesic there. Why free boundary? Well, because each of the points here in the interior, these are circles, right? And as I go to the boundary, the circles close up into fixed points, so I get an actual sphere. If I take a closed geodesic, something that goes around like that, that's going to be a circle worth of circles. So that's actually going to be a torus, okay? So that's what we're going to do in the next and last part of the talk. But for now, let's talk about two spheres. And of course, the free boundary geodesics I'm going to look at, they're not going to self-intersect because I wanted the spheres to be embedded, okay? So unfortunately, or fortunately, perhaps, the boundary is degenerate, right? As I said before, maybe before jumping that there, let me maybe remind you here that the boundary is degenerate, okay? The metric here degenerates. So V is identically equal to 0 on the boundary. So when I write this metric, it's degenerate on the boundary, all right? Maybe I have this written too many times now. So the existence of geodesics starting from the boundary is needs to be addressed, right? I can't use a normal exponential map, for example. I need to justify that such things exist, that I can actually shoot a geodesic inwards with in this setting. And so for doing this, let's maybe parameterize here the boundary with this curve beta. So beta if I'm using coordinates A and semi-axis A and D, so this would be A cosine S, D sine S. And let's say VS, like in the picture, is the unit normal, okay, with respect to the metric G check. So the inward pointing unit normal at beta S. And I parameterize in such a way that this is the 0 point, okay? So that would be the trivial solution that we're going to have in just a moment. So let's argue that I can actually shoot geodesics inside, that I can start a geodesic with that initial velocity. So here's a statement. For any S, there is a unique maximal geodesic which starts transversal to the boundary. And moreover, it actually satisfies that the initial velocity is precisely this unit vector. So this is saying that, for example, something like this cannot occur. If I start from the boundary, it must actually be orthogonal. And so there's only one through each point. Okay, so there's only one through each boundary point, the one going in orthogonally. So how do I prove this? So I want to use an argument that is inspired by a very beautiful paper of Haas, Norbury, and Rubinstein. So the first place where I saw this kind of argument using Plateau's problem is actually in this nice reference. So here's how the proof sketch goes. Take a point very close to the boundary, okay, in the orbit space. So if it's very close to the boundary, the corresponding circle upstairs, the pre-image, right, the G-orbit, it's a circle, but it's a very small circle, because if this point was to get even closer, these are fixed points, right? So this circle is shrinking as I go to the boundary. So it's a very small circle. In particular, it lives in the boundary of a convex ball, for example, upstairs. This means it's extremal, okay, for the Plateau problem. And it's also real analytic, right? It's a very well-behaved contour. So there is a unique solution to Plateau's problem. I can fill this in with a disk, a unique least area disk, okay, which is therefore minimal with that boundary. So the solution is unique because by extremality, it's smooth. It's also embedded. And by uniqueness, again, it's G invariant, because if I rotate the contour, it's invariant, right? So I get the same contour back. If the surface changed, I would have another solution. So any rotation must fix that, must preserve that. Therefore, this filling in is actually filling in, maybe I'll redraw it, is a filling in by circles, right? It's filling in by other orbits. So I can actually see this downstairs as a little curve downstairs. And by the fact that, well, I'm foliating here a disk with circles, there has to be a fixed point somewhere there in the middle. So it has to hit the boundary. Oops. It has to hit the boundary somewhere. Okay. Also remember that the symmetry reduction principle of Xiang-Lawson is an if and only if statement. So because this disk upstairs is minimal, so this guy here is minimal, its image downstairs is a geodesic. So I have a little piece of geodesic, at least, starting from the boundary at some point. Now, let's argue that it meets the boundary orthogonally. Well, that's because the disk is smooth. So if the angle here was not 90 degrees, if it came in at some angle, the disk upstairs would have a conical singularity with the same angle, and it doesn't. It's actually smooth, so it must meet at 90 degrees. Finally, there's only one geodesic starting from each boundary point, because if I had two, well, by the removable singularity theorem, for example, as stated in Choi Shun's paper, the two corresponding surfaces, the other corresponding surface would be a cone, right? And I can remove the singularity, so it would actually be smooth. They would actually have to touch there. It would be tangent. So they would have to be tangent. And then I apply the maximum principle, and you have two minimal surfaces touching that they have to agree, right? So there's uniqueness as well. Of course, I didn't prescribe that point. I prescribed this point, but you can imagine moving this point around And by a continuity argument, you see that you cover everything. Okay, so then you can go backwards and start from the boundary. All right, so that's the proof of the existence of geodesics. Now let's go back to finding free boundary geodesics, right? I know I can start from the boundary. I want to close up something that is, for example, like that. All right, that is 90 degrees on both sides. So in order to do this, I use some extra information. I have some reflections that I have left. Namely, I have reflections about x1 axis and x4 axis, which give me, in particular, some geodesics, the horizontal geodesic, as I'm going to call it, which is the geodesic gamma of 0, the one starting at beta 0, and the geodesic gamma vertical starting at beta of pi over 2. So that's gamma pi over 2. Okay. These geodesics, of course, they correspond to trivial solutions upstairs. They correspond to planar minimal spheres upstairs. This guy here corresponds to setting x4 to be 0, so that's pi 4. And this guy here, the vertical geodesic, corresponds to setting x1 to be 0, so that's pi 1. So we knew these were there to begin with, right? So now let's start from the boundary. So let's say this is beta s, and I start from there, and I hit this. Let's imagine I hit it orthogonally, okay? So if I hit the blue geodesic orthogonally, then I can reflect, and this must be the remaining part of that geodesic. It has to be this by uniqueness, and so it also has to meet the boundary on the other side orthogonally, okay, because it started orthogonal. So if I find some s, some values of s, such that gamma s looks like that, namely meets gamma vertical orthogonally, then by reflecting, I get something that I'm going to call an even geodesic, which is a special type of free boundary geodesic there. Another possibility is if I hit the boundary, if I hit the blue geodesic exactly in the central point, in this point O. Okay, so if I do something like this. So if I have some other beta s here and gamma s looks like that, and I hit exactly at O, then, of course, if I use now both reflections, this will reflect into something kind of like that, right? So it started here with a 90-degree angle, we'll hit there with 90-degree angle. So that's what I'm going to call an even, or rather an odd geodesic. And the one in black was even. Okay, so both of these will produce us minimal spheres upstairs. None of them are going to be planar because these are the only two planar ones. Okay, so we need to find these. We need to try to produce them. Okay, to do that, we'll use the following setup. First of all, let me argue that all of these geodesics starting from here, they actually go there. They don't just close up. Okay, they have to go there. This is basically a very simple topological argument because the horizontal geodesic does so, and these ones, this simple continuity argument. So let me maybe say they all intersect the vertical geodesic, the blue vertical geodesic, and they do so transversely, of course. Transversely, by uniqueness of geodesics with given initial conditions. And they actually do not self-intersect. All right, so something like this does not happen. Okay, so they all come from there and actually hit the blue geodesic somewhere. So let's say tau s is the first intersection point. First intersection point with the blue vertical geodesic, meaning it's the first point at which, when I look at the x1 coordinate, the x1 coordinate of that is 0. Right? Means I'm along this line. So this first intersection point, first intersection time is actually real analytic. You can show that with transversality. So both of these are real analytic functions, and so I can define real analytic functions like we had in the second part of the talk, which I'll call f even and f odd. Zeros of f even will be even geodesics. Zeros of f odd will be odd geodesics. And these are given by, well, I look at the tangent vector, right? So here I hit at that point, I have some tangent vector, and I see if that vector is horizontal, right? So that would be exactly when I have an even geodesic. Or I see the where it's hitting. What's this height, right? If that's 0, if I'm in exactly at that point, well, then we're in an odd geodesic. Okay, so zeros of both of these functions will produce minimal two spheres. And the horizontal geodesic in red is simultaneously even and odd for all values of A. That means that 0 is a solution for all values of A. So we can look for bifurcations from 0, as we discussed earlier on. Eventually, what I want to show is that the 0 sets look like in this diagram. The first one will be vertical, and I'll get to that later. But all of these other ones will go on to infinity. And so if I go further enough in A, I will get as many even and odd geodesics as I wish. All right. Another side observation, maybe I'll point this out later as well, is that even geodesics actually produce free boundary minimal disks as well, right? So if you take these geodesics that hit here orthogonally, I can just discard that part and just look at this positive piece. That's a hemisphere of ellipsoid, and these will produce minimal disks, okay? Free boundary minimal disks. All right. So we have the even and the odd problem. We wish to use Crandall-Rabinowitz bifurcation theorem that requires looking at both of these derivatives, the first, the linearization, and this mixed derivative. So these derivatives can be written in terms of Jacobi fields. Okay, to simplify our story, let's pretend that tau s is always equal to 1. I can reparameterize geodesics so that happens. And I look at these geodesics, this variation, let's say gamma s for s very close to 0. Remember that the gamma 0 is the horizontal geodesic there. So I can do that for positive or negative values of s. And I linearize these. I take the variational field corresponding to these. And so maybe let me draw fewer of them. And then I can perhaps, let's try to do this in white. I don't know if it will show. No, that will not show well. Let's try to do that in orange then. I have some variational field, okay, like that, which is a Jacobi field. So this Jacobi field has an endpoint value when I hit here the blue geodesic, and I'm calling that V of A for HT. If I compute VA at time 1, that's the endpoint value of the Jacobi field. VA prime is the derivative. So for the even problem, the linearization of the even problem is precisely this, okay? It's the derivative of the endpoint value of this Jacobi field. For the odd problem, it would be VA of 1 without the prime, all right? Similarly, the mixed derivative, dA ds, is dDA of that endpoint value. Again, for the odd problem, you repeat without the derivative, okay? You take this prime out. All right, so Crandall-Rabinowitz states that if this is 0 and if this is not 0, then that's sufficient for bifurcation. This being 0 means that the horizontal geodesic is degenerate at that instant. This being non-zero is enough to show that there's a change in the Morse index, and then a new branch of solutions is born. So to find these zeros, we look at an eigenvalue problem coming from that equation. If I write down the Jacobi equation, remember, this is a Jacobi field, right? Satisfies a Jacobi equation. If you write that down in coordinates, you get a Sturm-Liouville type equation. The functions p and q can be explicitly written, but for the purposes here, I don't need the exact formula. Let me just point out that p is 0 at the endpoint where the metric degenerates. So this is actually a singular Sturm-Liouville problem. So zeros of the linearizations of f even and f odd, here I'm collectively denoting them by f bullet, they correspond to lambda equal to 0 being an eigenvalue for this problem, okay? So the initial condition that you have there means that corresponds to the fact that you're departing the boundary orthogonally, as all the gamma s's do. And this corresponds to the odd problem. This corresponds to the even problem. So what one can show is that similarly to the non-singular case, you have a sequence, an intercalating sequence, sequences an odd and an even, such that at these instants, the linearization for the corresponding problem, even and odd, is degenerate. And if we look at the eigenvalue, so 0 is an eigenvalue, that's what it means. The eigenvalue changing sign there actually always crosses in the same direction. So if I were to plot the eigenvalues, so this here is A, this here is lambda of A, all of these eigenvalues are actually monotonically decreasing. Okay, they're decreasing functions of A. So if I were to compute this mixed derivative, that can be written as DDA of the eigenvalue as a function of A, and these numbers will all be negative. All right. Moreover, for a rather trivial reason, if B, C, and D are all equal to each other, then so all the semi-axes other than A are equal to each other, then the first bifurcation instant here will be also equal to that number. This is simply from the fact that if they're all equal, we're in the round sphere, right? And on the round sphere, this picture is actually not an ellipse, it's actually a circle, right? It's a disk, a round disk. And then vertical and horizontal are isometric. I can just rotate in that direction as well. It's the only instance in which I have this extra isometry, this extra Killing field. And of course, that's degenerate. So all of the gamma S's, all of these are solutions. They're all free boundary. And that's the reason why I have this vertical branch here. So this is a very degenerate case. This first bifurcating branch is actually, they're all isometric to one another. All right. But the fact that I have this 0 along the sequence and this not 0 along the sequence implies, by Crandall-Rabinowitz, that I have local bifurcation in all of these instances, right? So this is the first, this is odd, and the first odd instant, this is the first even instant, and so on. Second odd instant, second even instant, and blah, blah, blah. So I have a little bit of bifurcating branches at each of these. In order to conclude the proof, I need to show that these persist, that they actually go on to infinity. Well, this one will go up, but the other ones, for example, that they don't just attach to one another, all right? Okay, so that brings me to the last slide, or second to last slide. There's a bonus one. So before anything else, Rabinowitz's theorem that I discussed in part 2 has this assumption that the projection onto the parameter, so AS maps to A, that is proper. That comes, for example, from Choi-Schoen here, because these are 3 manifolds with positive Ricci curvature, so there's properness of the space of minimal surfaces with given topological type, compactness. So the projection is proper. Now, if I want to distinguish branches, I know that I have all of the degeneracy instants are labeled. I have all of them in this list. What I need to show that the picture is like that is just that they don't just reattach, right? That they don't reconnect. So for that, I need some invariants to distinguish them. And that invariant will come from a counting of the intersections with the horizontal geodesic. So let's say I take a geodesic like, draw a little bit better, like this, gamma, and I look at the positive part. So this just means x1 bigger or equal than 0. And I count how many intersection points I have with the horizontal geodesic. So in this case, I have 3, right? So and a gamma is equal to 3. So the claim is that if I have a 1-parameter family of geodesics, this number does not change, okay? A continuous family will keep that number constant. So this is locally constant. For example, this is true along all the bifurcating branches. And this is simply for the reason that if, say, these two were to come together and touch and disappear, well, in the limit, I would have touching geodesics, right? I would have geodesics that are tangent to one another, but they're geodesics inside a Riemannian 2 disk, right? So if they have the same initial condition, they'll be equal all over, and they're not. So so if I denote by BN bullet the branch corresponding to the AN bullet degeneracy instance, then it's not hard to see, using again Sturm-Liouville theory, that this number, this counting, is actually equal to, well, it's equal to 2n if n in the even problem, 2n in the even problem, and 2n minus 1 in the odd problem. Okay, so if bullet means even and if bullet means odd. So it actually parameterizes exactly the even and odd numbers, right? In particular, if I have, say, this one is the first even branch, so I have two intersections on this side, okay? Actually, sorry, I just realized you have just one, two if you count both sides, so I'm slightly off here. Let me take that away. All right, let me do this. So if I double this number, maybe I should have done that. So if let me upgrade the invariant here. Apologies for that. If I upgrade the invariant to count all of them, right? So I keep going on this side, and then I count all of them. So let me upgrade all of this. Then I have exactly 2n and n. Okay. So let me draw one example. Let's draw the second one. So I go down and up again. Okay. So I have 2 points. Okay. So this n a gamma is equal to 2. All right. Sorry about that. Now, so as I was saying, this one has 2 intersections, right? This one will have 4. Okay. So if they were to connect, if they were to attach to one another, I start with 2 and somehow I end with 4. Somewhere in between, this would be changing, but that contradicts this, right? So it's locally constant, so that doesn't change. That also shows that even and odd branches, even though they're solutions to different problems, they cannot cross. Okay? So they're disjoint. So they act as barriers for one another. Long story short, these are all disjoint in a very strong sense. And since we have properness and they're all disjoint, meaning none of them reattach to the trivial branch, they must all be non-compact by Rabinowitz. So they all must go on to infinity. And when I talked about properness, I guess I have to emphasize here other than, for values larger than this first instance. Of course, here, this is not proper, right? This goes off to infinity. The problem here is that I am looking at a piece of the space of minimal spheres, which is not the whole thing, right? And I am taking a slice there that kind of hides this fact. These are all isometric, and anyways, I'm not going to dwell on that too much, but maybe you can see that the projection away from this line is actually proper. So moreover, each of these segments, again, away from this first instance, so this here is A1 odd. Here I have to say A different from A1 odd. All of these other vertical segments must intersect the 0 set only finitely many times. And this is, again, by Choi-Shun, for example. So you only intersect by finitely many bifurcating branches. You can also show this by hand, since these are zeros of analytic functions. And so I get this count. If I count on the other side as well, I'm actually double counting because these are isometric. There's this reflection. But if I count, just say for positive S, I get this number of different minimal 2 spheres. So I get arbitrarily many as that goes off to infinity. Not only that, these geodesics, the values of S at which they start, so if this is gamma S, remember this is beta S, the value of S grows to pi over 2. So this starting point must go towards pi over 2. That means that this geodesic, for example, will eventually look like that, and eventually like that. So they will converge to the blue geodesic, the vertical geodesic. They will converge with a given multiplicity, exactly the multiplicity that self-indexes the branches. So these 2 multiplicities. That comes again from this count, okay? All right, so as I mentioned before, the even branches yield free boundary minimal disks. Free boundary minimal disks on hemispheres of ellipsoids. So really, to conclude this third part of the talk, I just wanted to mention one thing, which is, well, can we find these instances? Like, can we know what the values of these sequences, AN odd and AN even, can we know their values? Unfortunately, there's no closed formula. There's, however, an arithmetic equation involving infinite continued fractions that characterizes these instants. And that's using some special functions called Hewn functions. And they come from that Sturm-Liouville problem that I discussed, that singular Sturm-Liouville problem that I discussed. So we mentioned this in the appendix of the paper. It's a very interesting arithmetic problem. And even though we can't solve it, we have some numeric evidence that indicates that, for example, if I set all the other semi-x's to be equal to 1, so b, c, and d to be equal to 1, again, remember, we know this is 1 because that's a round sphere. We have very strong evidence that all the other ones are integers again. That, for example, even the second one, we don't know what it is, but we have very strong evidence that it's equal to 2. Namely, we conjecture that the nth odd instant is 2n minus 1, and the nth even instant is 2n in this case. Okay. There are some reasons to believe this conjecture other than the numeric evidence. For example, there's an analogy with closed geodesics on ellipsoids, at which closed geodesics bifurcate when their lengths are integer multiples of one another. Here, you notice the area of this planar minimal sphere from which solutions bifurcate, this red one, it becomes exactly an integer multiple of the area of the other sphere to which they converge at these instants. Okay, so somehow level sets of the energy function are crossing each other in a way that seems to be related to bifurcation. But as of now, this conjecture is a conjecture. All right.